Now we are. Okay. So if we try to find an antiderivative for this, we're not going to be able to. So, you know, the techniques that we discussed last time, which was, okay, last time we said, well, I could do the integral from 1 to b of e to a negative x squared dx, and then take the limit. Yes, that's fine, theoretically, but still the question is, how do we do this? And, you know, this was fine as long as we could integrate, because then we use fundamental theorem calculus, etc. But this is a function that unfortunately we cannot find an antiderivative of. So finding exactly what this equals to, it probably is out of reach. You can estimate, but it's out of reach at this point. But at least we would like to know whether this converges or maybe diverges. Even if we don't know what it equals to, but it would be good to know that this converges, for example, or diverges. Because then if you know that it converges, you go ahead and try to approximate. Okay? So this is what we are going to try to do. Okay? So we're going to learn a technique that will allow us to identify when an integral converges or diverges without having to actually compute it. Okay? Whenever possible. To do that, let me talk about a special type of integrals first, which is what we call p integrals. And they're going to be helpful to us in the next chapter when we talk about series. Okay? So we're going to come back to this question later. So let me go ahead and define p integrals. So definition of a p integral. So the p integral of type 1 is an integral of the form. So it would be the integral and then from a to infinity of 1 over x to the p dx. Okay? And typically, instead of a, we put a 1 in here. Okay? But in general, it doesn't have to be a 1. Okay? So where p is a positive real number. And then similarly, a p integral of type 2 will be the one from 0 to a. Okay? And then type 2 would be the integral from 0 to a of 1 over x to the p dx. And this, of course, a is a number that's greater than 0. And here also, a is greater than 0. Okay? All right, so this type of integrals, we call them p integrals, and these are very easy to analyze. So let's go ahead and let's analyze this in general. Let's figure out when is it that a p integral like this converges and when is it that a p integral like this diverges. And as you can see, as you will be able to see, it will depend on p. Depending on what this number is, you will know whether, just by looking at it, you will know whether it converges or not. Okay, same thing for this one. So let's do it. So convergence. And again, I want you to understand that if I put a 1 in there, it's essentially the same thing. So, for example, a is already bigger than 0. So note, if let's say if a is less than 1, remember it's always bigger than 0, then the integral from a to infinity of 1 over x to the p dx, we can rewrite this as the integral from a to 1 plus the integral from 1 to infinity. Okay? Now this right here, this is just a number, right? Because the integral from a to 1, there's no problem because a is positive, so this is just a number. You compute this integral as a number. So the convergence of the original integral really depends on the convergence of this one. Do you understand this? From 1 to infinity. So what I want to say is that it is enough to analyze this one. Okay? I want to get rid of the a. If on the other hand, a is bigger than 1, then the integral from 1 to infinity is going to be the same as the integral from 1 to a plus the integral from a to infinity. Okay? And once again, this right here is a number. okay, because that's from 1 to a, and then that means that the integral from 1 to 1 will converge if and only if this integral right here converges. In other words, the convergence or divergence of this integral is the same as the convergence or divergence of the integral from a to infinity. Do you understand this? So the point is that typically when we talk about a p integral, we think about it as from 1 to infinity, not from a to infinity. Okay? But it doesn't have to be 1, but it's enough to consider 1. And similarly for the type 2 case. So similarly for the type 2 case. Okay? So it is enough to study in the type 1 case. It's enough to study the integral from 1 to infinity. And in the type 2 case, it's enough to study the integral from 0 to 1. And that way we get rid of the a. And by what I mean by this is that whatever we decide for this one, it will apply if you had an a here, okay? And whatever we decide for the blue one is going to apply if you had an a instead of a 1, okay? Because they have the same behavior. And here we're looking for convergence, really. Okay, so let's go ahead and let's figure this out. So convergence of p integrals and let's go ahead and let's analyze type 1. So we're looking at the integral from 1 to infinity of 1 over x to the p dx. Okay. Now, as you know, this equals the limit as b approaches infinity of the integral from 1 to b of 1 over x to the p dx. And if you want to calculate this integral, it depends on p, okay? And really the difference is whether p is equal to 1 or not. Because when p is equal to 1, this is an ln. If p is different than 1, we treat this using power rule, right? Bring it to the top and then we use power rule. So we naturally need to split this into cases, okay? So let's first consider the case when p is different than 1, and then we're going to look at the case when p is equal to 1, okay? So if p is different than 1, then we have the integral from 1 to infinity of 1 over x to the p dx is going to be the limit b approaches infinity from 1 to b, and then I'm going to write this as x to a negative p dx. Remember, p is different than 1, so it's another number. So we write it like this, and then we integrate. All right, so this is negative p plus 1, and then we plug in from 1 to b. So that would be the limit as b approaches infinity. So negative p plus 1 is the same thing as 1 minus p, okay? So that's going to be 1 over 1 minus p times, and then I'm going to have b to the 1 minus p minus 1. Negative p plus 1 is the same thing as 1 minus p, okay? All I'm doing is plugging in b and then plugging in 1. And the 1 over 1 minus p, I put it in front. That's it. All right, how do we compute this limit? We plug in infinity for p, right? Okay. Then what happens?
Well, if that happens, then we have infinity to some power minus 1, which would still be infinity, right?
Well, what is this power?
Right. So it'd be close to 0. That's easier.
So this limit depends on this, okay? Because if this is a negative number, what happens if 1 minus p is negative? It means that this guy is really a 1 over something to a positive power, right? So when you have infinity to a negative power, that's really 1 over infinity to a positive power, so it's going to go to 0, yes? But if 1 minus p is positive, then what's going to happen here? The infinity survives in the top, and you're going to have infinity here as a result. Does Does that make sense? So if we want to calculate this, we need to understand what happens to 1 minus p. And here the point is, it depends whether this term right here is positive or negative. We know it's not equal to 0, because if it's equal to 0, then that would be with p equals 1, and p is different than 1. But this could be positive. When is this positive? In what case is this guy positive?
When p is less than 1.
When p is less than 1. If p is less than 1, this is a positive number, so the infinity will be on top, right? And you're going to have infinity for this limit, so the integral will diverge, right? When will this guy be negative? When p is bigger than 1, so 1 minus p is negative. So this is really a 1 over something, right? So you will have a 1 over infinity, because p goes to infinity. So this part goes to 0, so because it's going to converge to negative 1 over 1 minus p, or if you want 1 over p minus 1. Okay? So the moral of the story, I'm going to write all this. The point is that if p is less than 1, that integral is going to diverge. If p is bigger than 1, that integral is going to converge. Yes? Okay. So let's do the analysis now.
Is it bigger than 1?
I'm going to write it down. I'm just saying it so when I write it down, you understand what I'm saying. Remember, the whole point is the sign of this guy. If this is positive, the b stays on top, and therefore you get infinity. So diverges. When is this positive? When p is less than 1. If this is negative, then the b really goes to the bottom, so the infinity is in the bottom, so you're going to get 0, so it will converge.
Okay.
And that happens when p is bigger than 1. So this is going to be equal to, so there are two situations, right? So when p is less than 1, what happens when p is less than 1? What happens to this limit? So the b stays on top, so we're gonna get infinity, right? We're gonna get positive infinity, and therefore that means diverges. And then if p is bigger than 1, what's gonna happen? 1 minus p is going to be a negative number, right? So then this really goes down, so this is gonna go to 0. So you're gonna have negative 1 over 1 minus p. I'm gonna distribute the negative, so we get 1 over p minus 1. So converges. Do you understand this? Yes? Okay, so now the only thing that remains to analyze is what happens when p equals 1. So when p equals 1, we have the integral from 1 to infinity of 1 over x dx. So that would be the limit as b approaches infinity of this. Now this integral is ln, right? From 1 to b. So this is going to be the limit as b approaches infinity, ln of b minus ln of 1, which is 0. So that's just ln of b, right? So, and when the argument of the natural log goes to infinity, the natural log also goes to infinity, right? So this diverges here. Yes?
Why is it 1 over p minus 1? Wouldn't it be negative 1 over p minus 1?
No, negative 1 over 1 minus p. When p is bigger than 1, this is negative, so it goes to 0, right? So you will have a negative 1 here in this parenthesis.
Oh,
but then I distribute the negative 1 down here. So I flip it. Right. Yes? Okay, so putting all of this together, what does that mean? It means that the p integral of type 1 is going to diverge if p is less than or equal to 1, and converges when p is strictly bigger than 1. So let's put it together. So the integral from 1 to infinity of 1 over x to the p dx, then this one, it has the following behavior. It diverges if p is less than or equal than 1, and then converges to 1 over p minus 1 if p is strictly bigger than 1. Do you understand this? That's a summary of what we just discussed, okay? So diverges for p less than 1, and also for p equals to 1. So together, less than or equal to 1 diverges, and converges for p bigger than 1, and converges to 1 over p minus 1. Okay? All right. I mean, this is really not too relevant because most of the time you don't even need to know what it converges to, but we get it, so let's put it there. But what you really need to remember is that when P is less than or equal than 1, this diverges. When it's bigger than 1, it converges. Okay? That's the important result. This is the type 1, so now let's play the same game with the type 2. Okay? So, type 2. So type 2 is the integral from 0 to 1 of 1 over x to the p dx. Once again, we already know that it depends on p. So let's first assume that p is different than 1, and then we do the case for p equals to 1. Okay, when p is different than 1, remember the problem here is at 0. So we take the limit as a approaches 0 from the right of the integral from a to 1 of 1 over x to the p dx. So p is different than 1, so we can bring it to the top to use power rule. So we have the limit as a approaches 0 from the right of x to a negative p plus 1 over negative p plus 1 from a to 1. So as the limit as a approaches 0 from the right, so again, I'm going to factor out here 1 over 1 minus p, and then plug in 1 minus plug in a. So you get a to the negative p plus 1 or 1 minus p. And let's take this limit now. So again, here the limit is a approaches 0 from the right, so we're going to have an a in here. So we're going to have a 0 here to the 1 over p. So once again, it depends. This limit is going to depend on this power, right? If this power is positive, now this would just be a 0, right? And we're going to have a limit, and it converges. If this power is negative, what does that mean? It means that you really have 1 over a to the positive version of the power, so that bottom goes to 0, and 1 over 0 is infinity. Yes? And therefore it diverges. So the role reverses from above. Remember, above it diverged when 1 over p was positive. Now it's going to converge when 1 minus p is positive. Okay? So it's the opposite. Do you understand what I said? Okay. So again, to calculate this limit, it depends on p. If p is less than 1, that would make, so let me put it here in parentheses, that would make 1 minus p positive, okay? So this guy here will go to 0, and then we are going to get 1 over 1 minus p times 1. So we get 1 over 1 minus p. In other words, we get convergence. And then when p is greater than 1, then that will make 1 minus p a negative number, okay? So then this term right here is really a 1 over a to the minus that guy, so 1 over a to the p minus 1, if you will. So that bottom will go to 0, so we're going to have a 1 over 0, which is infinity, yes? So, and then this here will be negative infinity, but then because this is negative, negative times negative is going to be a positive infinity. So we get positive infinity. The point is that it diverges. Okay? So again, this part right here will give you infinity. You have a negative, so the parenthesis becomes negative infinity. But remember, 1 minus p is negative, so you're multiplying by something negative, so negative times negative is why it makes it positive. Okay? All right, so as you can see, it reversed. It was the opposite of what we got for type 1. Okay, for type 1, we got that it diverges for less than 1 and converges for bigger than 1. For type 2 is the opposite. Okay, and now let's analyze what happens at 1. So when p equals 1, we have the integral from 0 to 1 of 1 over x. So as the limit, as a approaches 0 from the right of the integral from a to 1. So as an ln from a to 1. And so this is the limit as a approaches 0. Now this time ln of 1, that's 0. And then we have our ln of a. Now, What happens when A approaches 0 from the right? The argument, think about the graph of the ln. How does the graph of the ln looks like? Good. So this is the ln, right? So when your argument approaches 0 from the right, what does the function do? It goes down to negative infinity. Okay? So it's a negative infinity, but we have a minus in front and makes it positive infinity. Okay? Bottom line diverges. So at 1, both of them diverge. Okay? So when p is equal to 1, both of them diverge. But then in the other cases, they are switched. So for the type 2, the summary is converges for p less than 1 and diverges for p greater than or equal to 1. So the integral from 0 to 1 of 1 over x to the p dx, what we get is converges to 1 over 1 minus p as long as p is less than 1, but it diverges if p is greater than or equal to 1. That's a summary. Okay? Questions? Do you understand this? All right. So again, we're going to be using this type of integrals as a tool to be able to identify convergence of orders. Okay? And again, later on when we talk about series, there will be a notion of p series. As you can imagine, it's going to be exactly the same idea. Just instead of an integral, you're going to have a series. Okay? And then the convergence of those series that will depend on p. And it's going to be just like what you're seeing here. Okay? All right. So let me do some examples. Determine convergence without computing. Okay, all we want to say is whether it converges or not. Determine convergence, and let's see, let's put the integral from 1 to infinity of 1 over x to the 3/2, then the integral from 0 to 1 of 1 over the square root of x, integral from 0 to 1 of 1 over x to the 3/2, and 4, integral from 1 to infinity of e. Okay, so the first 3 is to give you an illustration of the p integrals, and then the last one is to motivate the next discussion that we are going to have now. Okay, so let's see, how do we do something like this? Again, there is no need to compute anything, okay? You just have to look at it and decide. First of all, you need to be able to recognize, for number 1, that that's a p integral. What do we mean by p integral? It has a form 1 over x to some number, okay? So what's p here in this case? 3/2. So we recognize that this is a p integral. What's the type? P integral type 1 with p equals to 3/2. So does it converge or diverge? So as you know, be careful. We need to compare it with p, with 1, right? Whether this number is bigger than 1 or not. This is bigger than 1. 3/2 is bigger than 1. Yes? What do you know about p integrals of type 1 with p bigger than 1? Converge. You have in your mind still what you did for type 2. Remember, type 2 diverges for p bigger than 1. Type 1 converges for p bigger than 1.
No, I forgot how to use the less than greater than symbols for second.
Oh, okay. Don't overcomplicate things.
Yeah.
Okay. So converges, right? So this is a p integral of type 1 with p bigger than 1. So converges. Do you understand this? We did it in general. All we have to do is look at p and make a decision, depending on whether it's type 1 or type 2. That's what we have to do. Yes?
You have to plug 3 over 2 into the formula.
The question is just asking to determine convergence. I didn't ask you what it's equal to. If I ask you to evaluate it, then, you know, I wouldn't memorize the formula. If you really need to know what is it equals to, I would just do it because it's a very easy integral, right? We just do it. But the point is that once you look at it, then you need to know does it converge, does it diverge. That's what's really important. You can plug it into the formula, right? I think it was 1 over p minus 1. But we just care about whether it converges or not. Okay, good. But you see, for example, if I put a 3 here now, from 3 to infinity, that formula doesn't work anymore, because the formula works for 1. However, it still works the fact that it converges. You know, what we came up with when it converges or diverges, it applies for all cases. That was the discussion that I was doing earlier, that it was enough to consider this. But that little formula only applies when you have a 1. Because we got that expression because of the 1, right? If you have something else, then it will look different. So just compute it. If you really need to know the value, then you calculate it. But if you're only interested in whether it converges or not, it doesn't matter what number is in here.
As long as it's a number.
Yes, yeah, of course, it has to be a number. Yeah. You okay with this? Okay. So let's see the next one. What's the type? Type 2. And what's P? 1/2. Good. So you should rewrite this as the integral from 0 to 1 of 1 over x to the 1/2, you know, to see it. And then you immediately recognize this as a P integral of type 2 with P equals 1/2. And then we compare with 1. Is it bigger or smaller than 1? So it's less than 1. So now you go to our result. So what did we come up with? So when it's less than 1, it converges, right? So converges. Remember, when we say converges, what we're saying is that equals a number. When you take the limit, it equals something. You want to know what it is? You compute it. Or in this case, that formula works, right? Questions? Okay. About number 3. P integral type 2 with P equals 3/2. This time this is bigger than 1. And in the type 2 case, we know it diverges, right? Good. Questions? For example, the one that we introduced, remember when we introduced these ideas, we used 1 over x squared, right? And then we got that the type 1 case, it converged. That from the one that was from 1 to infinity, we got that it converged, and it makes sense because p is equal to 2, it was less than 1, it was bigger than 1. But in the type 2 situation, from 0 to 1, we obtained that it diverged, and indeed it does because it was bigger than 1. Okay, type 2. All right, so you will see how this is going to be helpful in a second. But now let's go ahead, and here is another integral from 1 to infinity of e to the negative x squared dx. And we would like to decide whether it converges or diverges.
Okay. The ones that you can't tell.
No, this one you cannot compute, but we'll be able to tell very easily. Now, the point is that we want to use another idea, which is what I'm about to discuss now, and it's called the comparison theorem. So let me just give you some quick explanation. Imagine that you have two functions. Notice that this function is positive. E to the negative x squared, that's a positive function. Okay? So, and after all, what we're computing there is an area of an infinite, over an infinite interval, but you can think of that as being the area under the curve for the interval from 1 to infinity. Okay? So let's say that you have a function here. I don't know, the function is doing something. We don't know what's going on with them. And then, let me call it, let me put it here. Function f. And then you have another function here. Let's call it g. I don't care what happens before 1, but let's say that from 1 to infinity, in this particular case, but let me do it in general, actually. So at some point from a to infinity, we have this condition, the fact that the function f is always on top of the function g. Okay? So let's say that, let me do this. So let's say that we have a situation like this for which both functions are positive, so we can talk about area. And then the function g is always under the function f. Okay? All right. And let's say that the function g is a function that is pretty complicated to compute. Okay? That if you want to figure out the integral of g, you cannot, or it's super hard to compute. But the function f is kind of easy to compute, or it's something that you know how to compute. okay? If the area under the graph of f equals a finite number, what do you think we could say about the area under the graph of G?
Less than that.
It has to be a finite number, right? Because we know this is positive because it's about the x-axis, yes? And the area under f is bigger, right? If we know that the function f gives you a finite area, in other words, if the integral from a to infinity converges for f, what can we say about the smaller one? It must converge. It doesn't make sense for this to diverge. Do you understand this? Now, on the contrary, not the big one, but if we know that the small one diverges, so if we know that this small one is already infinity, what can you say about the big one? It has to be infinity, so it has to diverge. That's called comparison theorem, okay? So how do you use it? Typically, you know, you're given an integral like this, and then you have a function that you really don't know how to deal with it, but then maybe you can find another function that you know how to deal with, and then you compare it with this one. And let's say that we have this comparison. If the top one I know converges, then the integral of the bottom one must converge. Just think about it in terms of area. If the bigger area is finite, the smaller one has to be finite as well. Do you understand this? And also conversely, if the small one diverges, meaning the small one is already infinite, well, the big one is going to be infinity as well because it's big. Does that make sense? So I'm going to use that idea here. So I'd like to compare this function with something that I know how to compute. Now, of course, I want you to understand that this doesn't always go the way you want, because let's say that you find your comparison, you are interested in G, and you find F, but it turns out that F diverges. When you do the integral of F, it diverges. So the big integral is infinity. Can you say something about the small integral? If the bigger area is infinity, can you say something about the smaller area? You cannot, you don't know. It could be infinity or it may be finite. I mean, if the big one is infinity, it doesn't tell you anything, okay, about the small one. Only when the big one is finite, it tells you that the small area must be finite. Yes? Also the other way around. If the small one is finite, you don't know anything about the big one, okay? So you have to be careful when you use this theorem. I'm going to write down the theorem and all of that. But let's now use it for number 4 so you see it. So do you understand the comparison? So if I find another function to compare with e to the negative x squared, then I'm good to go. If the function is in the right place, okay? So what I'm saying is, I could find a function that's smaller than this one, so a g, imagine that that one is an f. And if the one that I find converges, it's not going to tell me anything about this one, okay? So you have to be careful. If you're looking for a small function, you need to know that it diverges. If you're looking for a big function, you need to be able to tell that it converges. Otherwise, it's not going to help you, okay? Yes.
How do you know when to choose a smaller or bigger function?
That's experience. That's experience. So that's experience, and sometimes you need to have a feeling. Once you start doing problems, you look at an integral and you need to have a feeling of whether that integral should converge or not. Okay. We're gonna do a couple more examples. I'm gonna try to give you clues on how you could develop this type of feeling. Okay. But again, practice is the one that's gonna give you this. All right. Yes.
How do you come up with smaller functions?
You see in the example. Again, that's experience. What we're gonna do now is pre-calculus stuff, even less. It's just algebra what we're about to do. Now we're gonna mess with inequalities. Okay, so this really depends on the function that you are given. Okay, on the function that you're given. I'm gonna give you some tips depending on the type of functions that may show up. For example, this one. Okay, what I wanna do is I'm not gonna use a p integral, but at least I would like to compare this with something that I know how to integrate. And what's the thing that's in the way of me allowing me to integrate this? It's a square right here. If I didn't have this square, I can integrate this. Yes? This is just e to a negative. If I didn't have the square, it would be e to a negative x, and this is easy to integrate.
Oh, no.
Do you understand this? So I would like to compare this with e to a negative x. And let's see, what happens. It's also important because we're dealing with inequalities now. We need to know what's going on with x. Notice that we're integrated from 1 to infinity. So whatever we write, x is bigger than 1. Okay? So note, actually, let me say here, in this discussion that we have here, if the integral from a to infinity of f converges, then the small integral converges as well. Okay, that was a discussion that we were having in here. I'm gonna take advantage of this. Okay, so back to the problem. So here, know that x is gonna be greater than or equal than 1, since our interval of integration is the integral from 1 to infinity, right? Is our interval of integration. Okay, so because x is greater than or equal than 1, then what can we say about x versus x squared? So what can we say about x versus x squared? Which one is bigger? X squared, right? So when you have a number less than 1, you square it, gets smaller. Like 1/2 squared becomes a quarter. So it gets smaller. But if it's bigger than 1, it's going to get bigger, right? So we have that x is less than or equal than x squared. So now I'm going to multiply this by -1 because I don't want this. I want negative x squared, right? I want to compare with negative x squared. So multiplying everything by -1. Remember, when you multiply by -1, you need to flip the direction of the inequality. So we get that negative x is greater than or equal than negative x squared. Yes? Are we okay so far? Okay, and now I'm going to take exponential functions. Now remember, if a function is, what does it mean for a function to be increasing? When a function is increasing, it means that it respects inequalities. So if you have that input 1 is smaller than input 2, then the output of 1 is going to be smaller than the output of 2. That's what it means to be an increasing function. Okay, if x1 is less than x2, then f of x1 is going to be smaller than f of x2. As you go from left to right on the x-axis, you go from bottom to top on the y-axis. That's what it means to be increasing. The function is going up, okay? So that means that it's going to respect inequality. So because e to the x is, the exponential function is increasing, right? E to the x goes up, then if I apply exponential, it's going to respect this inequality. If your function is decreasing, it flips inequality, okay? It flips inequality. All right, anyways, since e to the x is increasing, then we obtain that e to a negative x is still greater than or equal to e to a negative x squared. Because you see, since this input is bigger than this one, if I do e to this number, I'm going to get an output bigger than this one, right? Because that's what it means to be increasing in respect to inequality. Okay, so and notice that both of these guys are greater than or equal than 0. So these two functions, they satisfy the condition of our discussion above, in which this guy will be our g and this one will be our f in the discussion above. Because e to a negative x squared is always below e to a negative x, at least on the interval from 1 to infinity. Do you understand this? So I'm going to attempt to use this idea that we discussed, provided that we get that this converges. If this diverges, then we cannot say anything and we need to go and look for another function. We just cannot use this, okay? But if we get that this converges, then we're good to go, okay? So let me just say, so if the integral from 1 to infinity of e to a negative x dx converges, then we can deduce that the other one must converge as well. Okay, by the discussion that we just have. So let's go ahead and let's concentrate this one then. And why? Because now there's something that we can compute. So let's compute. All right, so integral from 1 to infinity of e to a negative x dx. This is going to be the limit as b approaches infinity of the integral from 1 to b of e to a negative x dx. That's the limit as b approaches infinity of negative e to a negative x from 1 to b, which gives us limit as b approaches infinity of negative e to a negative b plus, because it's minus minus, e to the negative 1. Right? So you have a minus, but then another minus. Okay, so when b approaches infinity, up here, what are we going to have up here?
We have a negative number.
So negative infinity, right? And what happens when the argument of the exponential approaches negative infinity? Think about the function. Remember, think about the function. How does e to the x? You need to know how these functions look. E to the x, natural log, the inverse tangent, because it's going to help you to find limits. They show up a lot in your integral, so this is going to help you when it comes time to find limit. How does e to the x looks like? So it looks like this. Let me just write it down. So e to the x looks like this. You need to know this, okay? So when the argument b to the x approaches negative infinity, what happens to the function? Approaches 0. So this time it's going to negative infinity, so it approaches 0. So this part right here is 0. So what is this limit? 1 over e, right? E to a negative 1 or 1 over e. We don't really care about the number. Well, the number is an upper bound. It's a bound for the integral that we want. So it means our integral cannot be bigger than this one, but it's not equal to this. So it just cannot be bigger than this number. But what we really care about is the fact that this one converges. And because the big one converges, what can we say about the small one? It must converge as well. Okay? So, by comparison, the integral from 1 to infinity of e to the negative x squared converges. And we didn't have to compute that one. We computed an easier one. Okay? It's just that we found that the easier one was bigger than this one. It converged, so we can deduce this. Yes?
So we could then approximate that integral from 1 to infinity of e to the negative x squared. We can approximate that as less than 1 over e.
Yeah, now we can say that whatever this is going to be less than 1 over e. Exactly. Questions? For example, let's see, let's take a peek at it. So, yeah, I changed so that the people that on the other side can see it. So it was from 1 to infinity.
You go to scientific view, there's integrals.
Yeah, but this is so nice that you can type to it in natural language and it recognizes. I mean, this is Wolfram Alpha is super nice. You will see. And I'm typing in natural language. You see, integral from 1 to infinity of
I've totally never used it.
e to the e to the negative x squared dx. You know, you can. There are many things that you can just type it in natural language and you will recognize it. You see? Okay, so you see, this is the error function, whatever. So you know, this is not a standard function that we have discussed. So, the point is that this is about 0.139403. Let's do 1 over e. So, and then.
So I assume on a test or in the homework, we won't have to approximate it.
No. This is just, you know, for.
Unless 1 over e is equal to that.
So you see, I mean, it's not a good approximation. Look, 1 over e is 0.36, etc. And this one is 1.13, etc. But we know that 1 over e is bigger than this, right? Mm-hmm. So if you want to get a good approximation, when we discuss series, actually, we know how to approximate this. But we need to talk about series first. So one of the applications that we can use for our discussion of Taylor series later on would be that then you would be able to compute this using series. And you'll be able to approximate it with whatever accuracy you want. What do you want? The first 4 decimal places, you will be able to do it. So, okay.
Also, like,
but we'll do that at the end.
we do series before the test, there's always easier ways to do this stuff.
Show it work.
So okay, anyways, the point is that yes, you can take that as a first step of at least you know that whatever you compute is not going to be more than 180. Okay, it turns out that it's 0.13 whatever, but we will. Okay, so back here. Did you understand what we did? Of course, if you remember from Car 1, do you remember the squeeze theorem? When you were computing limit. It's a similar situation. It's just that you needed to come up with two functions, one from below, one from above, and they both have the same limit, and then the one in the middle, even if you don't know what's going on, is forced to have the same limit. It's squeezed between the two. The problem was in coming up with those two functions, right? That's the same thing that's happening here. We are making a comparison. If you want, we have two functions, just that the bottom one is always 0. Okay? So you just need to figure out another function so that when you compare, if that's what you need. But that's most of the time that's difficult figuring out the right function to use. Okay? So I'm gonna write down the statement, and then we're gonna do some examples, and hopefully you will get some feeling of some situations in which it's worth considering comparison theorem. Okay, some stuff going on. Just writing notes too slow. Okay.
That was all stuff that you had asked us for class he was responding to.
Yeah, I realized it was a while ago. But again, I don't look at the chat. So.
I saw you, Franklin. You're good.
All right, but are you okay now?
Didn't tell the professor he had questions.
I mean, they were all answers that we all.
Are you okay now, Franklin?
They were questions. They were.
Yeah, he was answering the questions, the rhetorical questions that I was making. Yeah. Okay, good. So then let's go ahead and let's focus. I'm going to write down the statement of the theorem that we just discussed, and then we'll do more examples. Okay. So this is called comparison theorem. So or comparison test. So let me write it down. Theorem. That's the comparison test. And here are the conditions. So you need to have your two functions. They have to be continuous, and they must be positive. Okay. So let f and g be two continuous functions. Be two continuous functions on the interval from a to infinity, and assume that they are both positive and g is always under f. Okay, and assume that g of x is less than or equal than f of x for all x in the interval from a to infinity. Then the crucial observation is that because they are both positive and f is always above g, of course the area under the graph of f is bigger than the area under the graph of g, right? That's the crucial observation. So then if we integrate, the inequality is respected. Okay. And then because of this inequality, then we have some deductions to make. So we can deduce that if the big one converges, then the small one must converge. Conversely, or equivalently, which would be the contrapositive statement, if the small one diverges, then the big one must diverge. Okay? So number one. So and then we have this, and number one, if the improper integral of the big function converges, then the small one converges. And number two, this is what I'm about to write is equivalent actually to this one. If you have taken a course in logic, have you taken discrete math? Any of you? No? So basically, for example, if I say, if it is Tuesday, then it will rain, that's equivalent to say, if it doesn't rain, then it is not Tuesday. Those two statements, they mean exactly the same thing. So this one right here, so basically what I'm saying is when you have a statement of the form P implies Q, this is the same as saying not Q implies not P.
I've had that before, but I can't remember where.
Yes, yes. So those two statements are logically equivalent. So this one is of the form P implies Q. So P is the integral of F converges and Q is the integral G converges. So if F converges, if the integral of F converges, then the integral of G converges. The contrapositive, which is equivalent, says the negation of Q. So what's the negation of this? If the integral of G diverges, then the negation of P, the integral of F diverges. So they actually mean the same thing. So I could only just write this one and then be done with it. But I'm gonna write both, okay? But I want you to understand that number 2 is exactly the same as number 1. It's just that it's being said differently, okay? So if the integral from a to infinity of g, this time the small one, diverges, then the big one diverges. So keep in mind that I'm not saying anything about what to do if the big one diverges. If the integral of f diverges, you cannot say anything about g, okay? Similarly, if the integral of g converges, you cannot say anything about f. Do you understand this? Yes.
So if we get a function, we find a function f. So let's say we were given just the function g, and we find another one, which ends up being f. If f of x then diverges, but we then need to find a new function to compare.
You have to find something. Yeah, that means that f is just it's not good for what you're doing. So look for something else.
So the answer would then be g of x is unknown or something.
No, it just means that the function that you found is not good. So look for another function. Okay. So yeah. Again, remember these are tools that you have at your disposal. Always try to see if you can compute. But then if you see that it's very difficult, it's going to be a hassle to compute, then try to see if you can do some sort of comparison. Unless the question says use the comparison theorem. If the question tells you that, then you know that you should be able to look for a reasonable function to compare. Okay? And it's good that you start thinking about this because we're going to be doing a lot of comparisons when we get to series. Okay? So now you already get your mind set for this, so when we get to series, it should be easier. At least you are used to seeing. All right, anyways, let's do some examples. I'm going to show you how we can make comparisons. So examples. Again, same question as before. Determine convergence. And let's see, let's do the integral from 1 to infinity of 1 over x to the 5 plus 1. And notice that I know this statement for type 1 integrals, and in the book it's also written only for type 1 integrals. The thing is that we need the function to be continuous, okay? Because in type 2 the functions are not continuous. However, this statement you can adapt it, and then a similar statement holds for type 2 integrals, provided that the discontinuity is as we typically do, not inside the integral but in one of the limits. If the problem of the type 2 integral is in one of the endpoints, which is normally what we do, we will break it up. If that's not the case, then a similar statement applies. Okay? So, but we're gonna be using this most of the time in type 1 cases, because the type 1 case is the one that's needed for series. The type 2 case is not gonna show up in series. So that's why we kind of focus more on type 1. Okay, this one. Let's see, what do you think the answer should be? Let's start to develop the field. Yes?
Well, the answer, whether on a convergence or what function we would use.
What do you think? What are you expecting? What are you expecting? Are you expecting this to converge or diverge?
Oh, wait. Oh, to infinity.
Let's see. When you see this, what comes to your mind?
Well,
A P integral. Look, when we're going to infinity anyway, right? So when x is very big, because our interval is from 1 to infinity, right? So when x is very big, do you really think that this plus 1 is making a difference in the behavior of this function versus 1 over x to the 5? Like, if you are a millionaire and I have $1 less than you, technically you have more money than me, but is that really, does that really matter, plus minus $1, right? So this function at infinity should behave very similar than 1 over x to the 5. Do you understand what I'm saying? So if we know what happens with 1 over x to the 5, we should expect a similar thing with this guy. So why is it good to do this analysis? Because what do we know about the p integral with p equals 5? This is type 1. It converges. So we suspect that this should converge. So if we want to use comparison, what do we need to do? We need to aim for a bigger function. Now we know that we should be looking for a bigger function because you have to make a decision. Should I look for a bigger or for a smaller function? I suspect that this guy is going to converge, so I'm going to try to look for a bigger function that I can figure out that converges, and then prove my suspicion. Do you understand what I'm saying? So you should try to have. It's good to have a feeling beforehand because then you know where to look for. Should I look for a bigger one or for a small one? Yes. This one, for example, is easy. If we had a minus in here, it's actually complicated to do the inequality. If we have time, we'll do it with the minus later. Okay, anyways, the term convergence. So in this case here, I suspect that it will converge. So I'm going to try to look for a bigger function. And remember, when you have a fraction, the bigger the denominator, the smaller is the fraction, right? So if I want to look for a bigger function, I just need a smaller denominator. And what's the smaller denominator that we should use?
X to the 4th.
X to the 5th.
X to the 5th. I mean, you can use x to the 4th, but
Oh, right.
I use
Sorry,
X to the 5th.
Okay, yeah, sorry. Fairly smaller, but still
So
small.
that dollar
Okay.
does matter.
Say that again?
Yeah, it's like the
Dollar
dollar.
does matter.
Okay. Like I said, for the
Technically, it matters.
for the behavior, if you're gonna put it in a world record who has more, then you have +1, you have +1, right? But then once they exit the door, they say, it doesn't matter. Anyways, so here I want to compare with 1 over x to the 5. Okay, so I'm gonna compare with I'm gonna call it f 1 over x to the 5. And let me say here, indeed. So again, you need to provide, when you're doing, for example, if you're doing this in the test, you need to give me some sort of argument of why or justifying why you're comparing with this. Because you can put whatever you want in there, but you need to show me why it's gonna work. So for example, you can say since x is bigger than 1, actually it doesn't matter. Doesn't matter about x. The point is that x to the 5 is certainly less than x to the 5 plus 1, right? X to the 5 is less than x to the 5 plus 1, so when we flip them, the inequality reverses. So, and we can say less than or equal to. So 1 over x to the 5 plus 1 is actually less than or equal than 1 over x to the 5. And they are both positive. Here it matters that x is greater than 1. Because if you have a negative interval, then this could be negative, right? So remember, in the conditions, we need the two functions to be above the x-axis. Because we're actually using area to justify this statement, right? Okay, do you understand the inequality? Now, why is this helpful for us? Because now we know the big function is a p integral with p bigger than 1, type 1. So it converges, therefore the small one converges, right? That's it. If you wanted to compute this, technically you can do it. It's a rational function, but you need to factor this and use partial fractions. And good luck factoring this. I mean, you can factor it. At least you know -1 is 0, so you can do synthetic division, then you will get a degree 4 polynomial. You need to factor that as a product of quadratics, both of which have complex roots. So you're not going to find more linear factors, but technically you can factor that, and then you can do partial fraction. But you don't want to get into that, okay? It's going to be 10 p.m. and you're not done. While here, we do it in one shot, okay? So, okay. So what do we write? So now we know that 1 over x to the 5 is bigger, and then we say since the integral from 1 to infinity of 1 over x to the 5 converges. Now remember, because we're not doing any calculations, you have to justify everything you say. Okay? So it converges. We're making a claim here. Why? Why? Because it's a p integral of type 1. Remember, the type is important. Of type 1 with p equals 5 bigger than 1. You write that sentence, you are telling me why you are saying that it converges. Okay? Do you understand this? Okay, so since this guy converges, then by the comparison theorem, I'm gonna call it CT. Okay, so the comparison test, I'm gonna call it CT. And you can call it CT as well when you're writing this to me in the exam, for example. I will understand what you mean. Then by the comparison test, it follows that the small one, so the comparison, by comparison test, the integral from 1 to infinity of 1 over x plus x to the 5 plus 1 converges. Did you understand this? Okay, so moral of the story. If your denominator appears to be something like a p integral, like a p integral, you know, like x to some power, then you should be comparing with a function of that type. Okay. Now I want you to understand that if this would have been a negative one, if this would have been a minus one, x to the 5 minus 1, still we will expect convergence because again, plus 1 minus 1, it doesn't really make a difference in infinity. But then this argument that we did here is not going to work because now x to the 5 minus 1 is on the other side, it's smaller, right? So 1 over x to the 5 minus 1 is actually bigger than 1 over x to the 5. So you have to compare with something else. X to the 4 could work, or x squared could work, but you need to argue. You need to show that 1 over x to the square, the 1 over x squared, for example, 1 over x to the 4 is actually bigger than 1 over x to the 5 minus 1. You have to justify it, okay? And that's when it could get a little bit hard. If we have time, we're gonna do it, so you see, okay? But that's not calculus, that's just pre-calculus trick, okay? That you have to use. But let me give you other examples so that you see the other situation. But at least when it looks like a rational function, you can do that. There's another theorem that I could give you, but that theorem will show up in series again. So I'm just gonna give it to you in series, and then whenever an improper integral shows up, you can use that theorem again. So there is a variation of this which is called the limit comparison theorem. And the good thing about the limit comparison theorem is that it removes the need for you to do the inequality. The inequality is done for you by you calculating a limit. Basically says if you find another function and you take the limit, if that limit is a number, okay, if it is a number, then the two functions behave the same. Either both converge or both diverge. If the limit is not a number, then depending whether it's 0 or infinity, then you have this statement. But the good thing to use it is if you get a number, then they both behave the same. So with that theorem, even if it was minus 1, when you take the limit with this guy, you're going to get 1. They behave the same, and then that's all you need. So it's a little bit more powerful, and you hide the need for doing inequality, because a limit is actually an inequality, okay? So when you say that the limit of a quotient of the two functions is a number, you are implying that an inequality like this is being satisfied. But in series, we will talk about that. I don't want to complicate this too much anyways. All right, so let's see. Number 2, another one. Integral from 1 to infinity of 1 minus sine over x squared. For example, this is a case in which you really want to use this theorem because this is not something that you may want to try to solve by hand. Okay? Even if it's possible, I think it's not even possible to do it, but even if it was possible to do it, it's going to be a crazy integral. Like you have to do some crazy substitutions and so on. Because you have here the trigonometric function, the rational function with the top is trigonometric and the bottom is a polynomial. And they don't mix well together in this scenario. But it turns out that we can actually compare this very nicely. So we're going to use the same idea that you used back when you were using squeeze theorem. The point is that every time that you see sine or cosine, there's something that we know immediately. What do we know about that function? The function is always between 1 and -1, right? So we can take advantage of that to build our way up to the function. So here is the idea. I'm going to give you the sequence of steps that we're going to follow to come up with this. First, we're going to figure out a bound for the sine function. Once we have the sine function bounded, then we can control negative sine. Once we control negative sine, then we can control 1 minus sine. Notice I'm slowly building my way to the function, okay? And once I control 1 minus sine, then you just divide by x squared, and we're gonna have some bounds for this function, okay? So this is the logical sequence that I'm gonna follow. Yes?
What do you mean by control?
You will see.
Know what they have.
You will see. What I'm telling you is, once I know what this is, let's say, if I know that this is less than something, I will know what happens with this guy. If I know that this is between two things, I know this one is going to be between two other things. Same thing with this one, and finally same thing with this one. You're going to see. Okay? The point is that you start with the sine function, or cosine, if it was a cosine, because that's the thing that we know how to control first. And then, little by little, we're going to build our way up to the function. Okay? So if you get an integral that has a sine or a cosine, my advice is start with that guy. Okay? And then build your way up. All right. So let's see. So we know that the sine function is between -1 and 1. We know this, right? Now I don't care about sine, I care about negative sine, because that's what shows up in here. So I'm going to multiply everything by -1. So multiplying everything by -1, it tells me that then negative sine, once again, is between -1 and 1. So, technically, this becomes a 1, this flips, this becomes -1, this flips, but after all, just put everything around, and it's the same thing. Just think about it graphically. You have the sine function, but multiplying it by -1, that just means flipping it with respect to the x-axis is still between -1 and 1. Do you understand this? It's just going down like this instead of going up in the beginning. But it's the same thing. Okay, now that I have this, it's time to get this. How can I get 1 minus sine in the middle? Just add 1 everywhere. So I'm going to do +1, +1, +1. So that means that 0 is going to be less than or equal than 1 minus sine, less than or equal than 2. Do you understand this? And now finally, what do we need? X squared. So I just divide by x squared both sides. Now, because x squared is positive, you don't have to worry about flipping inequalities. If this was an x, you have to be careful. It's also okay because x is bigger than 1. But remember, if you divide by something negative, your inequality is flipped. Okay? But x squared is positive, so that's not a concern. If I divide by x squared, so I get that 0. So 1 minus sine of x over x squared is positive, and moreover, is less than or equal than 2 over x squared. Do you understand this? Okay? So now, because we got this one is bigger, this is something that we know how to compute. So we're going to deal with this guy. If this converges, then it's going to follow this one converges. Now, I want you to understand that this is going to be a constant times our p integral, right? So if the p integral converges, then this one will converge as well because it's just times a constant. If the p integral diverges, then this one diverges as well because it will be infinity times a constant, just infinity, right? So will this one converge or diverge? It's converge. P with p bigger than 1. Because this converges, what can you say about that one? It converges. If the big one converges, the small one converges. Okay? So let me write it down. So since so remember, I'm gonna first talk about the original integral. Since the integral from 1 to infinity of 1 over x squared dx converges, this is a p integral where p equals to 2, which is bigger than 1, p integral of type 1, p equals to bigger than 1, then it follows that if I multiply by 2, it will also converge, right? Then 2 times this integral, which is equal to this, Let's see, who can justify this two? Why? Why, if this converges, I can say that if I multiply by 2 is the same as this. In other words, why can I take the 2 inside the integral?
Because the x squared is still going to be increasing much higher than just multiplying by 2.
So the question I'm asking is, in an improper integral, I'm saying that I can put the constant in or out of the integral, like if it was a regular integral. Why can we do that?
Because no matter what the integral equals, no number multiplied by 2 will equal infinity.
Okay, but why is it equal? Maybe something else. Remember, what is this? This is just a limit, right? And a property of the limit is that you can take constants in and out of the limit, provided that the limit exists. So, right, if the limit does not exist, you cannot do that. You cannot take constants in or out. Now, we are saying that this integral already converges. That means the limit is a limit, and that limit exists. So you're free to bring constants in and out, however you please. And you're not going to change the behavior of the limit. Okay? So that's why 2 times this is the same as the integral of 2 over x squared. And because this converges, then this also converges. Okay? Yes?
Okay. So we can bring out the 2 because the limit exists, because it converges, right?
No, because this converges, I did it the other way. Because this converges, you can bring the limit, you can bring the 2 in.
Okay. All right. Got it.
Remember, this is a limit, right? This is the limit as b approaches infinity of the integral from 1 to b, blah, blah, blah. That limit is a number. So I can take this 2 into the limit because that limit exists. Okay? So that means that this, and the result is 2 times the limit. So that means that this one right here is going to converge as well. It's going to be equal to twice whatever this integral is, right? So because the integral of 1 over x squared converges, then the integral of 2 over x squared converges. And so by the comparison test, the integral from 1 to infinity of 1 minus sine over x squared converges. Did you understand this? All right, let's do one more. I'm gonna let you try it on your own, and then and I'm gonna take attendance as you work on it. So try the integral from 2 to infinity is 1 over the 5th root of x cubed minus sine squared. Again, so here is good to develop some sort of feeling, okay? So, for example, remember sine is between 1 and -1, right? So at the end of the day, whatever x is, that sine squared represents a plus or minus 1, up to a plus or minus 1 to the entire expression. So once again, when we are at infinity, that plus or minus 1 is not really making a difference. So we are expecting this function to behave like this one, 1 over 5th root of x cubed, which is 1 over x to the 3 over 5. That would be a p integral. So we are expecting this, converge or diverge? 3 over 5 is less than 1. What do you know about p integrals of type 1 with p less than 1? Diverge. So you're expecting to get divergence from here, okay? Now you just need to do the calculations to justify this. But it's good to build this intuition, okay? So again, to come up with your inequality, I'm gonna give you the hint here. You have sine of x, then you can figure out that actually is quicker, since we already did that analysis. It's quicker to compare with, this time I'm gonna call it g, with this one. Okay, I want you to think about how would you do that, because I think if you follow the steps from above, it's not gonna give you what you want. Try it. and then we're gonna do it together. Let me take attendance. But if you want, ignore my hint and then try to do it the way that we did the previous problem. And then we compare notes. Yeah? All right, this is gonna go from the screen. So again, I'm gonna take attendance. Those of you on Blackboard, just type here, okay? All right, so. Make that decision yourself. I mean, if you want to use the hint, yes, I claim that this will be smaller, but you have to justify. See if you can justify. Because the thing is that if you try to do this, if you try to play this game that we play here, you're gonna find a bigger function. But that bigger function is not gonna help you. Because since we suspect that our integral diverges, you're really looking for a small guy. You're not really looking for a big guy. Exactly. So we need a small one that diverges. So if you play this game, most likely you're going to end up with a bigger function, but that's not going to help you. Okay. So that's why it's good to develop the feeling. Okay. And here you can tell that this behaves like 1 over x to the 3 over 5, because when x is too big, when x is very big, this sign square is really not important. Because this is a plus or minus 1. And most, right? This is not going to do much to the function. So. Okay, again, once you do problems, you will start getting the feeling of this, that you have to do problems. Let me take attendance. Let's see. Any ideas? Yes.
So my reasoning was that sine squared, the range of it is from 0 to 1.
Okay, good.
So when it's x to the third minus sine squared, it's always going to be minus something positive.
Okay.
And even if we get the fifth root, that it's always going to make the denominator a little smaller, which makes the number a little bigger.
Very good. So the observation here is to realize that sine squared is always greater than or equal than 0, right? So because of that, x cubed minus sine squared is actually going to be less than or equal than x cubed, right? Because you're doing x cubed minus something that's not negative, right? And now the fifth root is an increasing function, right? So we can take fifth root and it's going to still respect inequality. So the fifth root of this, because it's increasing the function, respects the inequality. And now because the fifth root of x cubed is bigger, when I flip them and I do 1 over that, that's going to actually be smaller, right? So 1 over the fifth root of x cubed is actually smaller than 1 over this guy. Very good. And all of this we're dealing with is positive because x is greater than or equal than 2, right? So the reason why this is here is because x is greater than or equal than 2. So it's not negative. Okay, and now that's it. Now because this guy, we know it's a big integral with p less than 1, it diverges, so the other guy diverges. Good. So since the integral from 2 to infinity of 1 over the fifth root of x cubed equals 1 over, x to the 3 over 5, then we recognize it as a p integral of type 1 with p equals 3 over 5, which is less than 1, so this diverges. So since this happens, then by the comparison test, the original integral diverges. Okay. All right. Questions? Yes.
So I think you said it earlier, but I wasn't So to get to that function, what you started with was -1 is less than or equal to sine x, which is less than or equal to 1, right? And then you went through the
What?
process to get it to match, to get it close enough
What?
to.
No, not really. No. The point is that if we do that, you're actually going to end up with some. We can try, and then you will see. I think we're going to end up with something big. Here, the analysis was: look, sine squared is always positive,
Right.
or greater than or equal than 0, right? So between 0 and 1. So when you do x cubed minus sine squared, that's going to be less than or equal than x cubed,
Okay.
right?
Because there you.
Because here you're doing x cubed minus something positive.
Mhm.
So this is going to be less than x cubed itself.
Right. Okay.
Does that make sense?
Right.
And then that when you take fifth root, which is our denominator, right? When you take fifth root, it respects the inequality because the fifth root is increasing function. So you keep the inequality, and so when you flip them, you get what we need. We get that the bigger guy is now the smaller fraction, right? Because the bigger denominator makes a smaller fraction. And we're good to go. So we did this differently than what we did above.
Okay.
Okay.